Assalamu alaikum students. So today we are going to discuss another very important topic in thermodynamics, that is the concept of specific heat capacity. Heat capacity is important in a sense that this is one of those parameters which you can measure experimentally. So once you are able to find out the specific heat capacity experimentally, you are in position to find out other thermodynamic properties of that system as well. So we know that whenever a tiny amount of heat energy is added to any system, it causes the temperature of that system to rise. So the heat capacity is the ratio of heat added to the temperature rise. So the specific heat capacity of any substance is defined as the heat supplied per unit mass of that substance per unit rise in temperature. That is, if you have an object of 1 kilogram at 30 degrees Celsius, so the amount of heat which is required to raise its temperature to 31 degrees Celsius is known as the specific heat capacity of that substance. And we know that in case of water, the amount of heat required to raise the 1 kilogram of water by 1 Kelvin is of the order of 4186 joules. So the heat capacity uh, is always the ratio of heat added to the temperature rise, but this ratio is not well defined because it depends on the conditions on which the heat is added to a system. That is, we can add heat to any system by two means. That is, we can add heat to the system at constant volume, or we can add heat to any system at constant pressure. So let's consider a system um, at constant volume in which you are adding heat to any to this gas at a constant volume. And another important thing that you should know is that whenever we talk about gases, we are interested in molar specific heat, which is defined as the amount of heat required to raise the temperature of 1 mole of a substance by 1 Kelvin. So let's suppose that you have a cylinder which is fitted with a fixed piston, and you are adding a tiny amount of heat. So the amount of heat that you are adding to this piston is used to increase the internal energy of the system because this piston is fixed, so it is unable to move. It means that there will be no work done by the gas on this piston. It means that all the heat which you are supplying it used to increase the internal energy of the system. And from the first law, it means that there is no work done. It means that the all the heat supplied is used to change the internal energy of the system. So now let's discuss that you can also add heat to any system at constant pressure. Um, let U1 be the internal energy of this gas, and this in this case the cylinder is the fitted with a movable piston, which is not fixed. So whenever you are adding heat, it means which will this added heat will result in increase in slight pressure within the system, which will exert force on the piston, and the piston will move upwards. And since we are interested to keep the pressure of the system constant, it means that the volume and temperature will adjust themselves in such a way that the pressure of the system remains constant. So, what the difference in this case is that the heat added, the Q2 in this case, is not only used to increase the internal energy of the system, but it is also used to do some useful work on the piston. So in this case, it means that the Q2 must be equal to Q1 plus W, and we should also note that Q2, because these are same objects, so it means that the amount of heat which is required to increase the temperature of this gas from 300 to 301 Kelvin will be different. That is, you have to supply more heat when you have to keep the pressure of the system constant. Because in this case, uh, the gas is also doing work again on the piston. So it means that in order to increase the temperature of this gas by 1 degree, you have to supply more heat. So that is the Q2 must be equal to Q1 plus W, and Q2 should be greater than Q1. So the specific heat at constant volume is equals to Q1, whereas the specific heat at constant pressure is equals to Q2. And since Q2 is greater than Q1, so we can say that the specific heat at constant pressure is always greater than the specific heat at constant volume. And the difference of the specific heat at constant pressure minus the specific heat of constant at constant volume is always equals to a gas constant, which is equals to 8.3 joules per Kelvin. So this statement can easily be proved for diatomic or triatomic gases as well as for the monatomic gases. Uh, that is, the difference will always be equal to 8.31 joule per Kelvin. And one thing to note is that this difference, that is the Cp minus Cv is equals to R, only holds for the case of gases. It is different for the case of liquids and solids. And this the reason for this large uh, difference between Cp and Cv for gases is that the gases can significantly expand on heating. In contrast, solids and liquids hardly change their volume on heating, so that the difference between Cp and Cv is much less pronounced in case of liquids and gases. Moreover, it is an experimental observation that the heat capacity of gas or indeed any system is proportional to the number of the particle presence. That is, if you change the number of particles in any system by two times, it means the heat capacity of that system should be doubled. So that is so. Let's now move forward. As in case of at constant volume, we notice that there is no work done on that system. So in that case, the specific heat is at constant volume is defined as partial U by partial T at constant V. Since in this case, from the using the first law, that is dq is equal to du plus dw, and dw is equal to 0, it means that dq should be equal to du. The specific heat at constant volume should be equal to partial u by partial t at constant v. And you can also write the specific heat in terms of the entropy by using the definition of entropy. And similarly, the specific heat at constant pressure will be equal to partial U by partial T plus partial by partial T into the product PV. Since you are also doing the work in this case. So this sum, that is the U plus PV, is equals to H, which is known as the enthalpy of the system. And enthalpy of the system is basically the total heat content which is present in any system. That is, we know that H is equals to U plus PV. U is the internal energy of the system. PV is also basically the energy which is added, a part of energy of this system. Since we know that the pressure has a unit of Newton per meter square and volume has unit of meter cube, so you can easily prove that the product PV is equals to the units of product PV is equal to Newton per meter, which is basically a joule. So enthalpy, which is defined as which is noted by H and is equal to U plus PV, is basically the total heat content present in any system, and the change in enthalpy of any system can be found by just figuring out finding out the change in internal energy of the system and change in the volume in any system. So another two different important energies are the Helmholtz free energy, which is defined as F is equals to U minus Ts, and the Gibbs free energy, that is which is noted by G and is equals to H minus Ts. So uh, so these are very important energies in thermodynamics, and Helmholtz free energy is related to those systems which are present at constant volume, and Gibbs free energy is related to the systems which are studied at constant pressure. And we can also define the entropy or free energies in terms entropies in terms of the free energies. Just like that, let's consider a small change in this free energy dF. So it means that this dF will be equal to du minus TdS minus STD. So when the only form of work is due to the changes in volume, so any small change in the internal energy can be written as uh, du is equals to uh, dq, which is equal to TdS minus PdV. Since we know that ds is equal to dq over t, so you can write it as, so you can write dq as TdS. And from this equation, putting this value of du in this previous equation, you will have df is equals to minus sdt minus pdv. So it means that you can find the entropy of any system in terms of the free energy, which is equals to minus partial f by partial t. But this is the formula for the entropy when the volume of the system is kept constant. So it means that S is equals to minus partial f by partial t only holds when the volume of the system is kept fixed. And similarly, you can find out the pressure of the system at constant temperature, which will be equal to minus partial f by partial t at constant t. There is a mistake. So pressure is equal to minus partial F by partial V. So there should be V at constant T. So please make this correction. Similarly, the entropy can also be written in terms of the Gibbs free energy, and you can easily find out the formula uh, for entropy in terms of the Gibbs free energy just by considering a small change in Gibbs free energy, and following the same steps, you will find that the entropy is equals to minus partial F by partial T at constant P, and similarly the volume is equals to partial G by partial P at constant temperature. So that's it for the specific heat capacity. So now let's discuss a few important problems related to these chapters. We have all already discussed about the calculation of entropy for reversible and irreversible process, and we learned that the entropy of a reversible process is always zero, whereas the entropy of an irreversible process always increases. So we are going to consider a problem for the irreversible case here, and we are going to show that the entropy of an irreversible, in case of an irreversible process, is always zero. So the first case that we are going to discuss is that we are going to consider two systems at different temperatures, which will allowed to make contact and thermalize. So the question is, let's imagine that there are two identical blocks of materials which are held at constant volume with a constant heat capacity Cv. Constant heat capacity Cv means that the specific heat capacity is not a function of temperature. That's why we are calling it that the specific heat capacity is constant. So one object is at temperature of 320 degree Kelvin, whereas the other object is at temperature of 280 Kelvin. So you're interested to find out the entropy change of this combined system. And one important thing that you should note is that we are going to calculate the entropy change, imagining the reversible flow of heat. So once you are given this condition that you are allowed to calculate the entropy by imagining the reversible flow of heat, it means that you can integrate the entropy from some initial to final state. So now let's find out the solution. We know that one object is at 320 degrees Celsius and 320 Kelvin, and the other object is at 280 Kelvin. So it means that when both these objects are combined, the object which is at higher temperature will lose to the object which is at lower temperature. That is, the hotter body loses heat to the colder. So the total internal energy at temperature T is Cv dt. The internal energy is conserved so that the temperature of the two systems must be at 300 Kelvin. That is one, since one is at 300, 320 and the other is at 280 Kelvin, and both the specific heat is constant for both these objects. It means that whenever they will be in thermal contact, the final temperature of this combined system will be the average temperature of these two objects, which will be 300 Kelvin in this case. So it means that the final temperature of this the combined system will be 320 plus 280 divided by 2, which will be equal to 300 Kelvin. And since we are given that we are going to solve this problem at constant volume, there is no change in volume. It means that um, uh, the work done will be 0. So the entire the entropy change of the hotter object is which is losing heat is equals to dq over t, and dq as we defined is that can be defined in terms of the specific heat, which will be equal to cv dt. Since cv is equals to is defined as the ratio of the heat added to the temperature rise. So it means that dq is equals to cv dt, and the initial temperature of this hotter object is 320 Kelvin, and when both these objects are combined, the final temperature is at 300 Kelvin. So the change in entropy of this hotter object will be equal to Cv log of 300 by 320, and you will see that that this object, that is the hotter object, the entropy of this object is decreasing. And how you can figure it out? You know that here you have a log of 300 to 350, which will give you, and this will be a ratio which is less than 1. So the log of some decimal number is basically a negative number. So it means that the change in entropy of this hotter object will decrease. It means that it decreases its entropy as it loses heat. Whereas the other object, which is at low temperature of 280 Kelvin, it means that it is gaining heat. The entropy change of the colder body is equals to CVDT divided by T. So the initial temperature of that object is as 280 degrees Celsius at Kelvin, and the final temperature is 300 Kelvin. So this will be equal to Cv log of 300 divided by 280, and in this case we have a number which is greater than 1, and the log of 1 point something is a positive quantity. It means that the entropy change of this cold body is positive. It means that it increases its entropy. So we are interested in the entropy change of this combined system. So it means that the total entropy, the total change in entropy of this combined system is equal to the change in entropy of the hot object plus the change in entropy of the cold object, which will be equal to, which can be find out by combining this equation 1 and 2, and this will give you Cv log of 300 squared divided by 380 into 280, and you will have a value of 0.045 into CV. That is, the net result is an increase in entropy of this combined system. What we again learn from here is, what we can conclude here is that all irreversible process lead to an increase in entropy of the system. So there are two other cases in the book as well. That is when you are allowing the heat to flow allowing the gas to flow into the vacuum. This is also an irreversible process. So that problem I am going to give you as an assignment. So let's now discuss another sample problem. And let's consider that you have a 1 kilogram of glass brick, uh, which is heated at 180 degrees Celsius and then plunged into a cold heat bath containing 10 kilogram of water at 20 degrees Celsius. So assume that none of the water boils and that there is no heating of the surrounding. So what is the final temperature of the water and the glass? And secondly, you are given that the mass specific heat of the glass is approximately 750 joules. So what you are given that you have a glass which is whose weight is 1.5 kilogram, and it is at 180 degrees Celsius. The second object is water, which is at 20 degrees Celsius, and you are going to add this brick of glass into water, and you are asked to find out the final temperature of the system, and as well sorry, you are going to ask the find out the final temperature of the system. So how we can solve this problem? We can use the conservation of energy principle to solve this problem. What we know is that the total energy of the system will always remains constant. It means that the change in internal energy of the glass plus the change in internal energy of the water should be equal to zero. So, from the conservation of energy principle, we have that the change in internal energy of the glass plus change in internal energy of the water is equal to zero. And we can find out the change in internal energy of the glass by using this expression. That is, we know that the change in internal energy is defined as mc times delta T. So, you will have m into C for glass into T minus Tg, which is the initial temperature of the glass plus the final temperature, which is denoted by T here, plus the mass of the water, the specific heat of water, and the final temperature minus the temperature of water equal to zero. So, uh, the final equilibrium temperature T is same for both. So we solve for T and obtain an expression which will be equal to the. That is, you are what you have to do is that you have to solve this equation and you have to separate out this temperature dependence, which will give you a ratio of these two terms. So just plugging the values for mass, specific heat, and temperature for glass and water, you will be able to find the final temperature of this system. And what is not given here is the specific heat of water. We have also discussed about the specific heat of water, which is equal to 4184 joules per kilogram per Kelvin. So putting all these values, you can find out the final temperature of this system. So now let's discuss this final problem about the cyclic process in which you are asked to find out the total work done in this thermodynamic process. So this figure shows you a cyclic path A, B, C, D, A in this PV diagram of an ideal gas. So you are asked to find out that how much work is done on the gas during this cyclic process. So this is a cyclic process, and you are going to find out the total work done on the gas. So we know that the work done on the gas uh, is defined as minus P times delta V. And we also know that the work done on the system is equal to the negative work done by the system. Because if let's consider that if you have a gas in a cylinder and the piston is and the work is done by the surrounding, then it means that the piston is pressing that gas downwards. So that's the work done on the system. And similarly, you know that there is also a work that can be done by the gas. It means that it can expand, it can push the piston upwards as well. But that work will be negative in this case. It means that the work done on the system should be equal to the negative of the work done by the system. So since in this case you are asked to find out how much work is done on the system in the cyclic process, so we are going to use this equation W on the system is equal to minus P delta V. So let's consider the first interval that is from A to B. So during an isobaric, this is an isobaric process since the temperature of the system is kept constant. So from A to B, the work done on the gas will be equal to minus P2, which is the pressure at this point, into V2 minus V1. V2 is the final volume and V1 is the initial volume. And we know that that this final volume is greater than the initial volume, it means that the work done is negative in this case. And now from B to C and C to and E to A, these are two processes which are uh, happening at constant volume. And since there is no change in volume, we know that whenever there is no change in volume, the work done is zero. So it means that along B and C and D and A, there is no work done. So now let's finally find out the work done on the gas between C and D. So the work done between C and D will be equal to minus P1, because the pressure is P1 in this case, is equal to the final volume minus the initial volume. So the final volume is V1 in this case, and initial volume is V2. So V1 minus V2, and we know that V1 is less than V2. It means that this work done, if you write it in terms of V2 minus V1, uh, can be written as plus P1 into V2 minus V1. So the net work done on the gas in this case is equals to the work done along the AB path plus the work done along CD, which will be equal to minus P2 V2 minus V1 minus P1 into V1 minus V2, and you can also write it as a P2 minus P1 into V2 minus V1 with the negative sign. It means that the net work done on the gas in this case is less than zero. That is, it is negative. So this is I'm laying this on you to think about that why there is a negative sign. It means that uh, that the work which is negative should be greater than the positive work. So that's all for today's lecture.